This is one of the most famous pictures in all of mathematics, and it comes from an equation so simple it fits on a napkin. It started as a toy model of animal populations. How many rabbits next year? Based on how many you have now. Turn one dial, the growth rate, and at first the population just settles to a steady number. But keep turning, and it splits in two. Then 4. Then 8. And then suddenly, it shatters into pure chaos. A single innocent equation, containing an entire universe of order and disorder. Let me show you. Here is the whole thing. Next year's population equals r times this year's, times 1 minus this year's, where the population is measured as a fraction between 0 and 1, 0 being extinct and 1 being the absolute maximum the land can hold. The r is the growth rate, our dial. That 1 minus the population is the twist. It's overcrowding. When the population gets large, resources run out and it pushes back down. Growth pulling up, crowding pushing down. That tension is where everything interesting hides. Start with a small growth rate. Feed in any starting population. Apply the rule again and again, and the numbers march calmly to a single stable value and stay there forever. A low growth rate settles at extinction. Nudge r higher, and it settles at some healthy, steady population, year after year after year, the same number. Predictable. Boring even. If this were the whole story, nobody would have made a picture of it. But watch what happens as we keep turning the dial. Past a growth rate of 3, the steady value can't hold. Instead of settling on one number, the population starts alternating between 2. A boom year, a bust year, boom bust, forever. The single line has split into 2. Turn the dial a little more and each of those splits again. Now a cycle of 4 different values, then 8, then 16. These splittings, called period doubling, come faster and faster, crowding together as the growth rate climbs, racing towards something. And then, at a growth rate of about 3.57, the doublings pile up infinitely and the whole thing breaks. Beyond that point, the population never repeats. It jumps around endlessly, never settling, never cycling, looking for all the world like random noise, even though every single step is computed by that same simple rule. This is deterministic chaos, born from one line of arithmetic. The map from order to chaos is complete, but the deepest secret is hidden in the pattern of the splits. Measure how much dial you need for each doubling, and each gap is about 4.669 times smaller than the one before. Always. That number, 4.669, is called the Feigenbaum constant. And here is the miracle. It shows up not just here, but in dripping faucets, in electronic circuits, in heartbeat rhythms, in completely unrelated systems that double their way into chaos. Deep down, they all fall apart in exactly the same way. Even chaos, it turns out, has universal rules. One equation, one dial, and a journey from perfect calm through splitting cycles into unpredictable chaos, with a universal constant threaded through the whole descent. That is the strange beauty at the edge of order. Simple rules, endlessly deep behavior. This has been actually rendered. If this one drew you in, you know which button to press.